In the diagram, ABCD is a trapezoid. Angle DAB is equal to angle ADC, equal to 90 degrees. Also, AB is 7, DC is 17, AD is 10. Point P is on AD, Q on BC. PQ is parallel to AB and to DC. Point F is on DC, so that BF is perpendicular to DC. BF intersects PQ at T. Determine the area. Area of a trapezoid would be the top, which in this case is 7, plus the bottom, which is 17, all divided by 2, and multiplied by the height, which in this case is 10. So that looks to me like 12 times 10, and that is 120. Determine the measure of angle BQP. BQP, so this angle right here. Okay. All right. Is that the correct angle? Yeah, it is. All right. Well, since PQ and DC are parallel, right? PQ is parallel to AB and to DC. Okay, so this is parallel to that. So that means, based on those angle rules, that this is also theta. So I can use, and this is a right angle, so that's great. I can use tan. Tan of theta would be that BF over FC. Now BF is top to bottom, which is 10, because BF and AD are parallel, right? Does it say BF? What am I? BF and AD. Let's see here. Yeah, well, yeah, because they're both hitting at right angles, so that's why they're parallel. And then FC, well, AB and DC are parallel, so AB is the same as DF, so this is going to be 7. So therefore this would be 17 minus 7, so 10. So that looks to me like 10 over 10, which is 1. So if the tan of theta is 1, then that means theta is 45. If PQ is x, determine the length of AP in terms of x. Okay, so PQ, where's PQ? This whole thing, okay? So since this is 7 and P to Q is x, that means T to Q would be x minus 7, I believe. Yeah. And then since that's 45 and this is a right angle, right? Because PQ is parallel to DC, so BT would touch that at a right angle. That means this is theta also. Since, well, actually the better way of writing it is that theta is 45, so this is 45 also. That angle in there, 45 degrees. So that means that these two are the same. So that means BT is x minus 7. So determine the length of AP. Well, it's x minus 7 because AP is the same as BT. Yeah, I think that's all we can do there. D, determine the length of PQ for which the areas of trapezoids ABQP and PQCD are equal. Okay, so ABQP is the same as PQCD. Okay, ABQP, so that would be 7 plus x over 2 times the height, which is x minus 7. And then PQCD, that would be x plus 17 over 2 times the height, which would be 10 minus x minus 7. Let me just do it on the side here. 10 minus x minus 7. So that would be 17 minus x. Yeah. Okay, so that is the math equation, the algebra. And now we just need to solve this. Okay, so first let's multiply through by 2. That gets rid of the fraction. And then we have just this guy. So let's expand this now. So there'll be 7x minus 49 plus x squared minus 7x. And this would be 17x minus x squared plus 17 squared minus 17x. That cancels with that. And then this cancels with this. So all we have is, if we collect like terms, 2x squared and 17 squared plus 49. If I've done that properly. So that's 2x squared is 338, I believe. And then the x squared would be 169. And therefore x is 13. The rectangular region A is in the first quadrant. The bottom side and the top side of A are formed by the lines y is equal to 0.5 and y is equal to 99.5 respectively. The left side and the right side of A are formed by the lines with the equations x equals 0.5 and x equals 99.5 respectively. Determine the number of lattice points that are on the line with the equation y is equal to 2x plus 5 and are inside region A. Okay, so we're going to need some space here, so let's move this up. Let's draw x-axis, y-axis. And then we have these lines. So we've got this guy and this guy. Oh, this certainly is not drawn to scale, but you guys get the point. Y equals 0.5 and y equals 99.5. And then, of course, you've got the ones that are on the x-axis. So this is x equals 0.5 and x equals 99.5. So what's inside those black lines is region A. And then we have this equation 2x plus 5 that's going to run through. Okay, so when we got 5, and then let's see here, when x is, when y is, when x is 0, we have 5, and when x is 0.5, we would have 6. Is that right? Yeah, so 0.5 and 6 is going to be there. So that's this point is 0.5 and 6. So that's not a lattice point. Lattice point has to have integers. So let's try 1. When x is 1, this will be 7. So this is the first lattice point. So this guy, 1, 7. Yeah, 1, 7. And then we're going to keep going. This line, oh boy, I don't even know how to draw it because it's not going to be drawn to scale at all. But something like that, I think. Okay. Then we have to keep going until y is 99.5. So if I set 99.5 to y and then solve for x, let's see, what do I get here? I get, oh boy, 47.25 for x. So that means this point that touches that is 47.25 and 99.5. So the when it's 99, when y is 99, that's, I think we can get an integer. We'll get x equals 47. So I guess somewhere here, that point would be 47 and 99. So we will have all lattice points would be from 1, 7 to 47.99. So as long as the x value, as long as the x is an integer, we'll get an integer for y. So if you put x equals 1, x equals 2, all the way until x equals 47. So this looks to me like 47 points. And all of them, of course, will be inside the region A. So that's pretty much the solution there. Part B, for some integer b, the number of lattice points on the line with the equation y is equal to 5 over 3x plus b and inside region A is at least 15. Determine the greatest possible value of b. Similar kind of story here, but slightly different this time. So let's draw that diagram again. So we've got to put in those lines, and when you do, you get that region, right? That region A. And then this equation, 5 over 3x plus b, that is a line, obviously. And let me see here. When x is... Okay, so we want a lattice point. So that means the only way this is going to be a lattice point is if x is a multiple of 3. So x has to be some sort of 3t. That's the only way this will turn out to be an integer. Is b an integer? Yeah, b is an integer also. Okay, so for example, x can be 3, x could be 6, x could be 9, and so on, right? So for these guys, y would be 5 plus b. This would be 10 plus b. This would be 15 plus b, and so on. All the way till Well, x goes all the way till 99.5, correct? So it could go all the way till 99, which itself is a multiple of 3, and that would be 165 plus b. Okay. And that's a lot. That's, I believe, 33 values of x. But they are saying we want at least 15. So we want to figure out what is b when you only have 15. Okay. So that's sort of the thinking there. So let's plot this very, very, very briefly. It doesn't have to be accurate, but it's going to be something like this, something like that. That line, this line right here, it'll be something like that. So any point on that line, I'll just put a little point here, is going to be of the form x, y. Well, x is 3t, and then y would be, if you put 3t in there, it would be 5t plus b. Any point on that line. Okay, so let's talk about this now. So x is between 1 and 99, correct? In terms of the integer values. Now x we have set to be 3t, so let's put that in there. So if you divide through by 3, and you want to keep it as integers, then it would be t is between 1 and 33. Yeah. Okay, that's for x. Now what about y? Y is also the same kind of story. It was from 99.5 down to 0.5, but if you just look at the integers, it'll be the same kind of thing between 1 and 99. But y, what is y? Well, y is this guy, right? 5t plus b. And we want to figure out what b is because we don't know b. Okay, so let's actually just talk about it without b for a second. Since y is 5t without b, then if we divide through by 5, we're going to get, I think, what, about 19? Yeah. So that means that if b was 0, then this guy here would just be 5t, and we would have t between 1 and 19. So that would basically mean you'd have 19 values of t, and for each value of t you'd get 1 lattice point. Okay, that's pretty good progress because we want at least 15, so we got to keep going here. What happens when b equals 1? What happens when b equals 2? And I'll let you guys do that. But when you get to 24, you get this situation where it's 3t, 5t plus 24. That's the point now. And then now it becomes, instead of this guy here, it becomes 5t plus 24 is less than 99. And that is going to be 5t less than 75. And then when you divide through by 5, you get less than or equal to 15. And this gives you 15 values. And that occurs when b equals 24. So you have to sort of keep going there and get to a point where it's at least 15 for the number of lattice points inside region A. In this problem, you may choose to consider angles in either degrees or radians. Determine an angle for which sine x over 5 equals sine x over 9 equals 1. Sine of x over 5 is equal to the sine of x over 9 is equal to 1. So we have that sine graph. You guys remember, it kind of goes like this, right? It keeps on going forever. And this is x, and this is the sine of x, that axis. Okay, so let's talk about when is it 1, because we want it to be 1. Well, it's 1 right here at the very top. So this would be 1. So that happens when, and I always work in degrees, but there's nothing wrong with working in radians. So this is 90 degrees. And then this point is exactly 360 degrees later. So 90 plus 360, 450. And then it just kind of keeps on going. So in general, the theta, or actually we're talking x. Let's say x would be 90 plus some multiple of 360. So 360 times n, let's say. That's basically the answer. But they want a very specific situation, and they have these denominators. One is 5, one is 9. So that makes me think that, you know, you have to get a common denominator, which is 45. So both of those x values, well, there's only one x value actually. That x value has to be divisible by 45. So it's a multiple of 45. So I would basically take that initial 90 and just multiply it by 45, which would be 4050. And that would work. That would put it, if you put it in, you get the sine of 4050 divided by 5. And that's going to be equal to 1. And that's going to also be equal to the sine of 4050 divided by 9. And that's also going to equal 1. So I encourage you to try that out. And when you do, you should get the same result as I did. There are sequences of 100 distinct positive integers n1 to n100 with the property that for all integers I and j with 1 less than or equal to I less than j less than or equal to 100, and for all angles x, we have the sine of x over ni plus the sine of x over nj does not equal 2. Determine such a sequence n1 until n100 and prove that it has this property. So let's start off by letting this sine x over n I and the sine of x over nj equal to 2. See, here they're trying to show you up here that it's not equal to 2, but let's say it is equal to 2. And this ni and j, they vary, right? So we'll just call them m and n because they're going to vary based on the fact that I and j can be different numbers. So we'll just say this is sine of x over m, and we have the sine of x over n, and that equals 2. Now, you guys remember, I think I just talked about it, that the sine graph kind of goes up and down like this, right? Forever. And the maximum it can ever be, if this is x and this is the sine of x, is 1. So the only way that these two could add up to 2 is if individually they're both equal to 1, and therefore the sum would be 2. So that basically means that we have the sine of x over m would be equal to 1, and it means that the sine of x over n is equal to 1. So that means that x over m is 90, but it can be any 90 plus any sort of 90 plus any multiple of 360, as I had previously shown in the previous question. So I'll just call it r as to represent how many multiples of 360. And in the same way, x over n is also going to be 90, but instead of r, I'll use a different letter. I'll call it s. So if I divide through or multiply through by n, this is m, sorry, it'll be 90m plus 360mr, and this will be x equals 90n plus 360ns. And now since x equals both of these guys, we can set them equal to each other. So we have 90m plus 360mr is equal to 90n plus 360ns. Correct? And then when you divide through by 90, you'll get a much cleaner equation. You get m plus 4mr is equal to n plus 4ns. And this one I will call equation 1, because I will have to refer to it later. So we'll just call it equation 1. Just put that there, like that. So now what we need to do is we need to go back to the original question and think about what they're doing here. So let's read this again. There are sequences of 100 distinct positive integers, n1 through n100, with the property that for all integers I and j, with I less than or equal to 1 less than or equal to I less than j less than 100, and for all angles we have that this is not equal to 2. So what that makes me think is that this word is very, very important, distinct. We have distinct numbers here. So that means I've got to make sure that this can hold true even if the numbers are distinct. So let's work with that. So now I'm going to have to make some substitutions though. I'm going to let the m equal some power of 2. So 2 to the power of a, and times some constant, and let n equal another power of 2 times some constant. Now we're also going to make some assumptions here, that we're going to assume that c is odd, and also that this d is odd. And because we need distinct values, that a cannot be equal to that b. Okay, so we go back and we sub that into the equation 1, and we get 2 to the power of a c plus 4 times 2 to the power of a c times r is equal to 2 to the power of b d plus 4 times 2 to the power of b ds. Got it? Okay, so now let's divide by 2 to the power of b, and that will give me 2 to the power of a minus b c plus 4r times 2 to the power of a minus b c, and then this will just be d plus 4s. And therefore, if I bring the 4 over, this will be 2 to the power of a minus b times c plus, let's see here. This 4 I can combine with the power of 2, so r times 2, a minus b plus 2, since 4 is 2 to the power of 2. And then times that by c, and then minus that 4ds. So there should have been a d there. Okay, so now notice this, everything has a power of 2. So that means that this left side is even. And then d, well, we had originally made the assumption or set it as odd. So that's odd. So left side is even and right side is odd, so this falls apart. So therefore there's no values of r or s for which equation 1, this guy up here, is true. And if m and n, these guys, m and n, do not contain the same number of factors of 2, then no angle x exists that satisfies the conditions. So basically what we have shown is this whole thing falls apart if you try to prove it mathematically. So our original assumption, which I had done here, is false, that it cannot equal 2. So therefore, original assumption is false. So what that basically means is that the sine of x over m plus the sine of x over n cannot equal 2. Because here we had started off saying, oh, it equals to 2, and then after this big long song and dance, we showed that it's impossible. So it does not equal 2. So we've proven this part here. But now we have to determine a sequence. There's still more to the question. Okay, let's do the last part. So we need to figure out a sequence that would make this, would show that. So we have ni equal to, let's make it a power of 2. And then I, remember, is between 1 and 100. So for example, it would be 2 to the power 1, 2 to the power 2, 2 to the power 3, and so on, all the way to 2 to the power of 100, correct? Now, we need to get a pair of numbers from the sequence that contain the same number of factors of 2. But none of them contain the same. They all have different. So no pair of numbers from this sequence contains the same number of factors of 2. So that means that there's an angle that makes so there is no angle that makes that equal to 2. So therefore there is no angle x that makes the sine of x over ni plus the sine of x over nj equal to 2. For any I and j with this range that 1 is less than I, less than j, less than or equal to 100.